The ideal gas law equation is the most important equation of them all. And the reason why is because it helps you solve for pressure, volume, number of moles, or temperature. Now, let's talk about briefly about how we get to the ideal gas law. Well, let's look at Boyle's law. So Boyle's law talks about that the volume is inversely proportional to pressure. So this is like a proportionality constant. Looks like a alpha, but nevertheless, just pay attention to how they all come together to make the ideal gas law equation. So this is Boyle's law. Avogadro, we're just going to call it A, is that volume is proportional to the number of moles. And Charles' law, we'll just call it C, volume is proportional to the temperature. If you put all of these together, you make this relationship. Volume is proportional to the number of moles times T, and P, look at it, it's in the numerator, it's in the denominator. So that's the ideal gas law relationship. Or we're just going to call it the ideal gas law. Now, this is proportionality constant. You'll get, if you take an advanced course in thermodynamics, you'll get to derive this from scratch. This is what I did when I was an undergrad. But that's not the case here. This is way beyond the scope of this class. So what we're going to do is just simply kind of, okay, so how do we make this an equal sign? Anytime you want to make this an equal sign, go from proportionality constant to an equal sign, you have to find a constant, a number that you have to find, kind of like pi. So then it becomes like this, V equals N. This constant is called R right here, R T over P, which of course we can translate this into PV equals nRT. So a lot of you have seen this before. This is the equation that we will focus on. Now, let's tell you what R is. R can be in different numbers, and it's a constant that is always given to you. It would be 0.0821. That's a 1. Liters ATM per mole Kelvin, like that. So that's an ATM. We're going to use this, although it's available in kilopascals and torr, or millimeters of mercury. So let's, in case if it's given another unit, you have to use it in this case, for example, or another case, you would have to actually convert to the ATM, your pressure to ATM. So let's talk about this question right here. Incandescent light bulbs, those are the old light bulbs. They're still in existence, but the ones that we have right now mostly are LED ones. They're better on energy. So because their tungsten filament evaporates, weakening the thin wire until it breaks. So the reason why they burn out is because that tungsten filament, which is the element W, simply again evaporates. That's why they don't last as long. Well, the reason why once you break them, they no longer work is because there's argon gas inside these light bulbs. And argon gas is what we call an inert gas, meaning it does not react. So it kind of protects it or slows down the rate of the evaporation. Nevertheless, let's actually look at how we solve this problem. It says, what is the pressure in atmospheres of 0.136 grams of argon gas in a 75 mil incandescent light bulb. Good. So we're looking for P. Pressure is unknown. Therefore, we're going to need this equation. But before we start plugging it in, we have to be aware of one thing, is that we need N. That's the moles. But we're given grams. So what do you think we should do if we have grams? You might have guessed it right. We have to convert to moles. And we know how to do that by dividing by the molar mass. Also, this is in mils. Our R constant is in liters. So we have to convert mils to liters. So you should start with that. Let's start with the number of moles. So we have 0.136 grams of argon. You need to convert to moles, so you just divide by the molar mass of argon. So from the periodic table, go and find the molar mass of argon. And that will be 39.95. Let me show you here. Right here, 39.95. 39.95. Again, we know how to do stoichiometry. And that would give us 0.00, we need 3 sig figs, 0.00340. Mole of argon. Wonderful. Now the next thing we want to do is to convert from mils to liters. You have two choices. You can divide by 1,000 or move the decimal point 3 places to the left, 1, 2, 3. So that would give you 0.0750 liters. Good. So now we have N, and now we have V. R is right there on the top. It's a constant. It's always given to you. You shouldn't memorize it. Therefore, we are solving for P. And temperature, of course, we need to convert to Kelvin. So here's the temperature. T is going to be 20 plus 273. That would be 293 Kelvin. Here's temperature. So here's our equation. We may need more space here, unless you don't write as big. So it would be PV equals nRT. This is done, by the way, in the previous chemistry class in Chem 111 or high school chem. So this is only really a review. But I'm giving you a good example here. So we're solving for P. So each side has to be divided by V. And it would become P equals nRT over V. So let's plug in. We solved N for N, which is the number of moles. And that was this number right here. Let's use more space here. We need more space. Mole. The R value is right here on the top, 0.0821. Sometimes it's written 0.0805 or 06, but we'll just do that one. Liters, ATM. moles K. And temperature was right here, 293 Kelvin. And then volume was 0.0750 liters. Okay, so when we do this calculation, let's look at the units cancel out. Liters cancels out with the liters. K cancels out with K. Moles cancels out with moles, and we're left with ATM, which is what we need, or atmospheres. So the calculation would be, again, to multiply by the top and then divide by the denominator. And that would give us 1.09 ATM, which is close to the atmospheric pressure. Very well. Take a minute outside of this video or to talk about or to understand how a car engine works. It actually works according to the gas laws. It's about really pressure. So take a look at it and we may explain when we meet how it works. Oh, this one moved here. 1.09 ATM.